Yep.
All right, let's see if our scheduled host has shown up. Yeah, I guess he hasn't. So let's just start. I'll just go through this. I have to say that I just listened to the lecture recently, and I haven't had a chance to go through the detailed notes. But there's a lot in this lecture, and I'm sure that in the detailed notes, it goes much deeper. So.
Hey, Joseph, by the
Yes.
detailed notes, you mean the ones that they link to in the
yes, every lecture has both a PowerPoint presentation and a set of notes that goes along with it. And the notes are usually a lot more detailed than the PowerPoint presentation, which is, in other words, the PowerPoint presentation you can swallow in an hour and a half class, but don't think you're done, because the notes, the rest of the notes go much deeper into the material, and they're part of the class too. So, but today I won't go through the detailed notes because I've only just gone through the presentation, the video. So in this video, they talk about machine translation. Three things: machine translation is one part of it, and then the sequence-to-sequence architecture, and then the attention technique. And I think that the TA ABLC really presented a well-organized lecture. So, and that makes the work of going through the lecture a lot easier. So let's just go through this, go through the notes that she gave. And so the first part is she talks about the history of translation before neural machine translation, which is a new thing from 2014. So machine translation is, the task is to translate a sentence in one language, which is called the source language, to a sentence in another language, the target language. And as an example, to give the French sentence, l'homme est né libre et partout il est dans le fer. And the translation is, man is born free, but everywhere he is in chains. So this is from Jean-Jacques Rousseau, is a French writer. But the idea is, you're given the first sentence, and you don't know, you don't know how long the translated sentence is. It doesn't have to be the same length. That's what's the first thing you really set up and notice about neural machine translation, is it has to automatically decide when to terminate the sentence. So, a French sentence might be able to be expressed in fewer words in English, or it might need more words to be expressed in English. But the neural translation technique has to decide where the end of this, when to end, how many words to translate in the sentence. So let's see, let me move this. It's probably in the way. Are you seeing this toolbar at the top of the page? Yes, no?
No.
Oh, okay, good. I'm seeing it, so I moved it over.
Only the bottom.
Oh, you see it? Oh, yeah, yeah. Let's see. Can I do anything about that? Let's see. I put this in presentation mode, and I think that's the best I can do. Yeah, sorry about that.
I think it's fine.
Yeah. Okay, so yeah, so she goes through the history of machine translation. Apparently, it really began a serious effort in the early 1950s, when they first had primitive computers to work with, and the motivating idea was to translate from Russian to English, because Russia was our enemy, and we needed to be able to translate things from Russian. So there's a video showing this electronic brain that translates to English, from Russian to English, and it's interesting. We could watch it. Let's see. Let's see. I just lost focus. So let me stop sharing this. Start sharing that. Hold on. Let's see. I've lost my. There it is. Share screen. And I want to share this. Okay. Let's see. Am I sharing this video with the electronic brain thing?
Can't see the video now.
Can't see the video? Okay.
No, the slides. We are seeing only the slides.
Oh, you're still focused on the slides. Okay, I have to stop sharing on the slides and then go to the video. Sorry, it's taking a bit. Let's see, share screen. Let's see, there. How about now? Can you see the electronic brain video queued up?
Yeah.
Okay, I'm gonna play it. Let's see, I'm not hearing the sound. Are you hearing the sound?
No.
No.
You're not hearing sound. Okay, I have to share my sound. I have to share the computer sound, I think. Switch to the computer audio. I'm gonna abandon this project. It's a little 1-minute video, and it's just interesting. The thing that's interesting about it is that it shows how overhyped everything was even back then in terms of machine learning. I'm gonna go back to sharing the slides. Let's see. Back here. We back to the slides now?
Yep.
Yeah, thank you. Yeah, so they were saying that they were going to be able to translate millions of words per hour and so on, and but then she deconstructs it for us and says that at that time the systems were mostly rule-based anyway. They weren't really even based on AI. They were mostly using a lookup table to map Russian words and phrases to English, and they were using a computer to do this very rapidly. So that was then. Then she fast-forwarded it to the 1990s to the 2010s, where the field of statistical machine translation was being developed. And the idea of statistical machine translation is to learn a probabilistic model from data and a probabilistic model is always based on Bayes' rule. So the idea is to find the best English sentence Y given a French sentence X, and so you can set that up as an optimization problem, argmax of the probability of Y given X. And then you can use Bayes' rule to break that, to express that probability distribution, the conditional probability of Y given X, using Bayes' rules. Bayes' rule can be expressed as probability of X condition on Y times the probability of Y. So this is just a simple application of Bayes' rule. She notes that the first factor, the conditional probability of X given Y, is the translation model, and the second factor in the product is P of Y, which is the language model, the probability that a given sentence would occur in English. And she points out that is learned from monolingual data. Monolingual data, in other words, that's learned from just English. You just read the Wikipedia and you can figure out the probability of any given sentence or phrase or whatever. But the translation model, because it involves both French and English, needs to be learned from parallel data, and what she means by that is parallel French and English dictionaries or word corpus. All right, let's see. So how do you learn the translation model? You need a large amount of parallel data. Again, that means you need a lot of French. You need a lot of French and you need a lot of English corpus. And she points out that the Rosetta Stone, which is maybe the first triumph of language translation, had 3 languages on it. It had Ancient Egyptian, which nobody knew anything about. It had Demotic, which I'm not sure it has something to do with Greek, and it had Ancient Greek. So these 3 languages were, the idea was that this document was written in 3 different languages. The ancients thought it was so important that they wrote it down in 3 languages. And scientists were able to use that to actually crack open the Ancient Egyptian. They actually learned how to translate Ancient Egyptian just from the Rosetta Stone. We're starting from the Rosetta. Let's see, I think I saw a raised hand, Shamsuddin.
Yeah. So my question goes to issue with parallel data. So in SMT, the parallel data is done by human manually?
Sorry?
So in SMT, does
Yes.
creation of parallel data done by human manually to say that this is the meaning of this manual translation?
Yes, I believe that's what the implication was, is that they created human beings sat down and put huge amounts of efforts into creating lookup tables between words and phrases. I mean, basically, the first step would be to take an English-Russian dictionary and just input that into a computer.
Okay.
English-Russian, Russian-English, and then to be more refined, you can start taking Russian phrases and translating them, and then putting that in adding that to your lookup table, and then you could expand it to sentences and put that in your lookup table, and so that was the starting point.
Okay, cool.
Yeah, good question. Okay, so and now the key feature, one of the key features in statistical machine translation is alignment. Like, how do each of the words in the source sentence align with the words in the translated sentence? And so she introduces this term, that P of X and A given Y, that is where A is called is alignment. It's called alignment. And I don't think she ever mentioned or made this clear, but I think alignment is actually a matrix that that has the words from one sentence as the columns and the words from the words from the English sentence as the rows or whatever, and the words from the French sentence as the columns, and that's clear here. So here's the sentence you want to translate English to French. Japan shaken by 2 new quakes. And then le Japon secoué par 2 nouveaux séismes. Pardon all my French, please. And she points out, you can map the alignment using a matrix like this. And then you find, for example, that the first word in the translation, in the translated sentence, didn't have any counterpart. So it's sitting all by itself. It has no counterpart in English. But the other words essentially align word by word with between the two sentences. And they call this the one that sticks out that isn't related to anything in the source sentence. They call that a spurious word, words that have no counterpart. Okay, and then she points out that the alignment can be many-to-one or one-to-one or many-to-many. So here's an example of many-to-one where the balance was the territory of the Aboriginal people, and then was the territory in English translates to appartenait in French. So it's 3 words to 1. Of the in English translates to O in French, and so on. So many-to-one alignment, one-to-many alignment. So in some instances, an English word needs more than 1 French words to translate it. And they have a special terminology for a word that needs a lot of other words to translate it, and that's called a fertile word for one-to-many alignment. And so here's how it would be represented in an alignment matrix. Let's see. And then there's this hilarious sentence in French that she introduces, il m'a entorté. He hit me with a pie. And it turns out that entorté, hit with a pie, has 4, it needs 4 words. This one French word needs 4 English words to translate it. So that's interesting. And they call that a fertile word, very fertile word. Okay, and then again, many-to-many alignment. So sometimes, N words on one side need M words on the other side to translate. So here we have the poor don't have any money. Les pauvres sont démunis. So don't have any money is translated to the single word démunis, but also any is connected with sont. I mean, sorry, have is connected with sont. It's don't have any money is translated to be sont démuni. So 4 words need 2 words to translate. That's the many to many alignment idea. And here's how it looks like in the alignment matrix. Okay, and so this probability, this probability P of X and A given Y, is actually being learned in statistical machine translation. So this is the problem again, the SMT, statistical machine translation, and the central problem is to compute the argmax of this quantity, the conditional probability of X given Y, given the probability times the probability of Y. And remember, Y is the translated sentence, and X is the source sentence. Okay, and then she says, okay, how we do this? There's one way you could try, which is brute force, which is to enumerate, every possible Y and calculate the probability given that. And of course, that's too expensive because you have to go through the entire dictionary. And so the answer is to use some kind of a heuristic search algorithm to find the best translation. You don't want to go through all the hypotheses. You don't want to go through all the possibilities. And this whole process is called decoding. And here's a German sentence translated to a French sentence. Geht ja nicht nach Hause. He does not go home. Let's see. I'm not sure how to. Let's see. I'm not sure what the lead through of this slide is, how it goes. I guess the idea is you're trying several possibilities 2 at a time. So you're trying to translate 2 words at a time, and you come up with several ways to translate it, and you keep those in mind, and then you take the next 2 words and come up with ways to translate those. You do it 2 by 2, and so you end up with a lot of different paths to get to a translation, and you go through all the paths and figure out which one is the best path. And we're not specifying how that's done, but the point is that you're working through a number of hypotheses, and some of them are dead ends, and you find the best one. So again, back to statistical machine translation, the history. So it was a huge research field. It produced a whole academic cadre of language experts, domain experts, and the system that they were the ones that built all of these machine translation systems that were very complex, many details, subcomponents, lots of feature engineering. And as we said, they needed to maintain a lot of resources, like lookup tables and so on, a lot of human effort. So it was a huge effort. It was fairly successful, but it was a huge effort to maintain it. And then all of a sudden in 2014, a paper came out that introduced neural machine translation, which is using neural networks to do the translation, and basically bypassing all of the need for domain knowledge for language translation. And this paper introduced sequence-to-sequence architecture involving 2 RNNs. And because of Stefan's great sessions, the last couple of sessions, we now know how RNNs work. So, so this introduces the sequence-to-sequence model. So the sequence-to-sequence model has 2 parts: the encoder and the decoder. The encoder takes in the source sentence, and it takes in the word encoding from the source encoder. So, you could have word-to-vec encodings, or you could have glove encodings, glove embeddings, or whatever. whatever your technique is, you're going to convert these words into numbers, and those numbers, the word encodings, are going to be the inputs to the encoder. The encoder is an RNN, and the output at the end, the hidden state output at the end, is then passed into the second piece of the seek-to-seek network, which is the decoder. And the decoder takes the hidden state from the encoder as its input. It takes a start token as the input, because we don't know what the input should be for the first. The token that begins a sentence is always start, and then at each part of the RNN has an output, and that output is then passed to the next as the input to the next time step in the RNN. So that's how the decoder part works. This is this is how you this is why why translation is an unsupervised task, because, well, it's basically a supervised task, but you don't need any labels because you already have the labels. The labels are just the words that you create. So he becomes the input to the second time step. Hit is the output of the second time step. It becomes the input to the third time step, and so on. So you end up with this translation. Il a m'entarté translates to he hit me with a pie, and the network actually comes up with the end token. So it's automatically decided how many words it needed to make the translation. That's what's
one
yes.
comment is the feeding that you point to is only at inference time. At
yes.
training time, that loop is open.
That's right. That's what she brought out in the next. I think
it's
one
there
of the next.
Even on this slide, because if you look at the pink, it says that the pink box.
Oh, the pink box. Okay, that's a good point. So this is test time is in other words, when you want to predict and you have your network already trained, then you give it a sentence and it will be able to predict the next. So this is a trained network with the pink lines, but in training you don't make this connection. I must say, I'm a little bit confused about what you do when you train. Because
I think during training,
so you have the output words in the other language. That's why the parallel documents are still needed in.
Okay, so it isn't completely unsupervised.
No, it's not unsupervised.
Yeah,
it
that's
is
correct.
The training, there is a slide for training. I think it's 2 slides on.
Yeah, it's later on.
You.
Yeah. Let's see. Okay, so this is a slide for training. So so we're given this. We're given the target. So I erred. I made a mistake. It's not, language translation is not unsupervised. To train the model, you do need to have parallel translations going in, and so so you're given this sentence, you're given its translation, and then you compute a loss function. You add up all of the terms from the loss function, and this loss function is being minimized during training. So let's back up and make sure that we got the rest of the slides that come in between. Okay, so she points out that sequence-to-sequence modeling is like a paradigm in NLP, but it can be used for a lot more than just machine translation. A lot of NLP tasks can be implemented as sequence-to-sequence tasks. Summarization, so you give it you read a Wikipedia article and you come out with a short summary. That's also seek-to-seek because you have the input and you have an output in the same. Now, in this case, it's in the same language, but it's still a translation of the. It's basically a translation of the article from English to English, but in a shorter way. Let's see, dialogue. You're trying to produce dialogue between 2 characters. So given one sentence, you want to predict the next sentence. So that's also a seek-to-seek sort of type task, because you're given something and you want to produce an equivalent, or you want to predict sort of an equivalent or something that comes next, I guess, from a language model. I'm not sure what parsing is. Can anybody chime in and indicate what parsing means in this context? Yeah, I'm not sure about that. And then another interesting example is code generation, where you have a task that you can express in natural language, like find all the prime numbers less than 100, and then you can write, and then that task gets translated into a Python code that actually carries it out, so that's another area where sequence-to-sequence modeling can be useful. Yeah. So, well, let's see. So she says that the sequence-to-sequence model is a conditional language, is an example of a conditional language model. The idea is a language model means that the decoder predicts the next word. That's what a language model always does. You give it a bunch of words and it predicts the next word. And it's conditional because its predictions go in one direction. They're conditioned on the words that came before it. So neural machine translation directly calculates the answer to your language translation problem by expressing it expressing it as a conditional probability that you can then decompose into all the previous states that went before it. So if you want the probability of y given the translated sentence y given the source sentence x, you can decompose that as the product of the first word given the first word of y given x times the probability of the second word given the first word and x times the probability of the third word given the first and second words and x, and so on. So you can actually write this down as a sequence of factors. And so then the idea is, how do you actually do this in practice? And the idea is you have to have a lot of input. You have to have a big parallel corpus, and what that means is you need lots and lots of French sentences and English and their counterparts in English. So that's the idea. You need a lot of input in order to train this thing. So this is the training slide that we looked at before. Again, we would get this from our parallel corpus, and we would input, many sentences with their translations, and then train this loss function, minimize it, and then once you're done, you have a trained model. Both of these RNNs are trained, and then you can go back to this slide where in inference, once you start with a trained model, in inference, every word output from every successive word that gets output from your trained model gets inputted into the next time step of the RNN. All right. Yes. Question?
Can we do NMT translation without using parallel corpus?
No, because you can't get something from nothing. You have to have, just like the Rosetta Stone, you had to have, in order to translate ancient Egyptian, you couldn't just translate ancient Egyptian from nothing. You had to have parallel corpus. You had to have it, the same text in Demotic and the same text in Greek in that case.
So it also involves some kind of manual feature engineering. So
yeah, somebody had to produce this parallel corpus. True.
Okay.
Yeah. So
but no feature engineering. What parallel corpus actually means is just a text document. For example, a Bible in both the two languages, or a legal document in both languages. So you're not manually feature engineering. It's just that those documents which refer to the same subject and are same at, you could say, the sentence or the paragraph level or at the document level are originally authored by humans. Okay. But you're not doing any feature engineering.
Yeah, okay. And somebody had to put it together, and that was a lot of work. But yeah, so this is so basically the idea is that language translation requires zero, well, it could require zero domain knowledge. In other words, all of the linguists are now put out of business, almost. Except, as we saw when we looked at Jeremy's lecture on from the Fast AI NLP class, sometimes domain knowledge is helpful. Like when you go from, when you translate, it's helpful to know something about the language that you're translating to. For example, Turkish has some, I forget what it's called in technical terms, but you can build phrases on top of each other by changing the word, and you can change the meaning of a word in many ways by adding more and more suffixes to it. So in English, you know, you can add one suffix, but in Turkish you can add like a suffix on top of a suffix on top of a suffix, and then it changes the meaning of the word, or adds nuances to the meaning of the word.
I recall he calls it agglutinative.
Ah, yes, agglutinative.
Yes.
Agglutinative. Thank you, Srinivas. So yeah, so that's where you accumulate more and more nuances of meaning by adding more and more things to the end of the word. And I think Jeremy mentioned that it's useful to know that when you want to translate any language into Turkish. But in general, you don't need, you can translate with zero domain knowledge between languages. And some of the exercises we did in that class, in the Fast AI class, you know, you translate a document from, you know, English to Vietnamese or whatever without knowing anything. And the translation may or may not be great, but at least it's a start.
Joseph, does she
yes.
talk about like what could be the, I mean, how does the label data look like? Is it sentence, I mean, so one sentence in English and one sentence in French, or is it paragraph?
She doesn't go into that detail, and I don't know the answer, but as Srinivas alluded to, it could be sentences.
It's just mainly
it could be
at this level,
paragraphs.
it's sentences, Gautam. It's sentences to sentence, because that's what you, you know, you make your RNN, the decoder or the encoder, kind of the longest sentence in the document you have, and then you go from there.
Okay. So does she talk about...
the point I also wanted to make was to the earlier question. In this case of translation, you start off with two sets of embeddings, two sets of vocab, and a common, and you know, a document which can go from one language to other, or a common source doc, or a parallel corpus. So it's all of the above: two embeddings, two vocabs, and a parallel corpus.
Yeah, so there is a link, a website, Opus. I shared in the chat. So they obviously provide free parallel corpus and for different languages. So you can select the target and source language so that you can download the parallel corpus.
Oh yeah, that's a very nice website there. And I think that I've seen, I don't know a lot about this, but I've seen things like paragraph to paragraph and document to document encoding too. I think they do that as well. So you can start out with a corpus of documents that are you know, English, a corpus of English documents and their equivalents in French. And so instead of the sentence as the unit of, it could be the document as the unit of that's going into the decoder and coming out of the encoder.
But Joseph, don't you think that would be really difficult, because the last hidden state has to kind of remember everything that it has seen, right? Only then it would be able to translate properly. Even a sentence, it seems crazy that it works, because it has to remember everything. Like, he hit me with a pie, it has to remember like it's a he, and like it has to remember everything, right? So
yeah, I think it's brought up as one of the disadvantages actually later.
Pardon?
I think this.
Yeah, it is brought out. That's right.
Yeah, yeah.
She calls it a bottleneck. But then the solution is given towards the end of the lecture, and the solution is attention, because you know, in the past, I think you're right. It would be a real problem to try to take one document as a unit and translate it, and be able to translate documents as a unit, because of this problem that things at the beginning of the document, you have to maintain all the connections between things that are distant from each other inside of the document. Words that are at the beginning of the document and words at the end of the document might be, you know, hundreds or thousands of words away. But the mechanism of attention, I think, makes that possible. I'm not sure that it does it perfectly, but it makes that possible at least. Let's see. Okay, so now they talk about decoding methods, and she talks about greedy decoding, which is when you just take the first possibility and you say, that's it. You know, I've come up with a translation. I'm going to take that and run with it. And each time you just take the most probable word that appears and go with it. That's greedy decoding. It's easy, but you can miss a lot of things because you could get on a false track. You could sort of go down a false track and then find and get yourself to a place where there's no good next word, you know, and you try to translate something and it doesn't come out well. We've all seen Google Translate fail spectacularly. Yeah, this is an example. So you're translating he hit, and then he hit is the most probable next word, but now you can't go back. You've made the decision to go with now you have to figure out what the next word has to be, and it's going to look awkward if you keep going with this. There's no good way to get a good translation of this sentence. So that's the first problem that you have to solve. And she says, all right, you could solve it by brute force, like she said before. You could try to compute all possible sequences. That would work if you had infinite amount of compute time, but we don't, so that one's out of the question. So now they introduce the solution that people do adopt, which is called beam search. So the idea is that you keep track of the k most probable partial translations, where k is an integer, and partial translations are called the hypothesis. K is called the beam size. In practice, around 5 to 10, she says. So you can score a hypothesis. A hypothesis is a sequence of words that you think are, that you think might be the right one. You can calculate a score from its log probability, and all the scores are negative, so higher scores are better. And so you search for the highest scoring. You look for high scoring hypotheses, and you track the top k of them on each step. So it does have a lot of compute overhead, and it's not guaranteed to get the best solution, but it's at least doable. And she gives an example where you use k equals 2, and so you're trying to, let's see, I'm not sure what the task is here. Let's see. Oh yeah, it's the same one. He hit me with a pi. So you start out with he, and then hit or struck. So you keep struck, and then you score them. Struck has a lower score. Then the next one is a, hit a. That's the most likely word to come after hit are a and me. And so you see now you keep this as you keep this in the realm of possibility. You keep the me around. It's a little bit more probable than a, but then the following word, he hit a, tart and pi. Tart has a low score, so you abandon it. You keep going with pi, and then at the end you end up with, so some hypotheses hit a dead end. I'm not sure right from here. It's not clear how you decide whether you hit a dead end.
You don't just hit a dead end, you just keep top two.
So
it ends after that, right?
No, you're just keeping the top two. So if you look at all the probabilities along the line, along the columns, minus 2.8, minus 2.5, minus 2.9, minus 3.8, you're keeping the highest two.
Yeah.
So the highest two is minus 2.
But I mean, the question is, how do you know when you hit a dead end? And I think
if you look at the 4 numbers, your k is equal to 2. So at each given column, you want to keep only the top 2.
Oh, okay. So here you got
the top by top in this
sorry,
case,
top two values,
the top,
right?
but
Sorry.
it means the highest scoring.
Yeah, highest
the highest one, yeah.
Yes, the highest
So,
two. The highest
right.
two.
Right, but what about here? Hit and struck. Why did we
But they
stop
drop
here?
out because the highest two are A and me, minus 2.5 and minus 2.8.
Minus 2.8 is 2.9 is smaller, and minus 3.8 is even more smaller.
Okay, between pairs. Okay, so you pick the best pair at each step. Okay,
Not really. It's not a pair also. It's just any word along the column. If you just look at the words from top to bottom, the highest K words are kept. It doesn't
so you're
have
always
to be a pair.
you're okay. So you're always guided by the highest
Exactly.
of all the K. So in any column.
Highest K.
Right. So in this
That
case, me is the highest K, and that's the one that goes on.
No, but both
two.
A and me.
K equal to 2.
Oh, but we pick the highest two, right? So we allow the highest two to go on. We allow the minus 2.8 and the minus 2.5. Okay, right. And so same thing here. We have two words, and of these four, we only allow the highest two to go on, and so on. So we ended up with these complete translations, and then we can evaluate each one of these possibilities and find the one with the overall best score, and then that's the one you adopt. So let's see. In this case, there's one more. Let's see. I think. Oops. Yeah. So that's the end. So tracing backwards through, you find the one with the highest score all the way through, and then that's the one that you hit upon as your. That's the one that you identify as your translation. Okay. Stopping criterion. So in greedy decoding, you can stop when the model produces an N token, so there's no real decision to make. But in beam search, there's different ways to stop. You can either say that we're going to stop that we're going to continue the beam search until we reach a certain time step where you decide that beforehand, or you stop when you reach when you have at least N completed hypotheses where N is also decided beforehand. So that's kind of like a hyperparameter that you have to decide beforehand which criterion you're going to use for a stopping criterion. So the idea is that when she talks about completed hypotheses, she means that when a hypothesis actually produces an N token, that hypothesis is complete. So here we must have, there must have been an end produced by one of these, by all of these actually, because these are all the completed hypotheses at the end here. So each one of these must have predicted an N token as the next one, and that's why these four are the completed hypotheses that we have to choose from. Okay, so there's two types of stopping criterions, one based on number of time steps and the other based on number of completed hypotheses, and you decide which stopping criterion you're going to use beforehand. Let's see. Oh, and then she mentions a problem, that is that if you're just going to go by scores, then you're often going to pick the hypothesis with the least number of words, because the smaller the number of words, generally the fewer terms there are in the probability chain here, and then the lower the score is going to be. So I'm sorry. Yeah. So longer hypotheses have lower scores, so that means that the shorter ones have higher scores, and you would tend to pick shorter hypotheses. Everything you try to translate, the translations that you pick would be dominated by the shortest translations, which is maybe not the best way to do it. So instead, you normalize by length, and that is this 1/t factor, and that helps to, and that mitigates this problem where you would tend to select the shorter hypotheses. Okay, so that finishes up beam search. Now she summarizes comparing the statistical machine translation with neural machine translation. I guess the number one reason why neural machine translation took over very soon after 2014 is that it performs much better. It's able to use the context around words. It's able to use similarities in phrases. It can be optimized end to end, and so you don't need to optimize individual components. I guess that was the case in statistical machine translation. When you optimize something end to end, you're getting the optimal solution, whereas if you try to optimize individual subcomponents, you're basically going to get a suboptimal solution, not necessarily the best one. Of course, less engineering effort, no feature engineering, as Srinivas pointed out. And you can use the same method in general for all pairs of languages. You know, if you figure out how to translate from English to French, then you can use that technique to translate from German to Swahili or whatever, any two languages you want. It's just the same technique. Disadvantages, NMT is less interpretable, hard to debug. I don't have experience with this to understand why this is the case. Anybody want to pitch in with a?
Yeah, I guess anything that relates to statistical compared to machine learning. So statistical approach is more interpretable compared to machine learning approach. I think this is the baseline issue.
Mm-hmm.
It's also the fact that you don't always clearly understand why a particular word was generated at a particular spot in time.
Yeah, with
so
statistical translation,
really, and I think she gives examples.
Yeah, I guess so. That's the point you said, the first gentleman. Yeah, in statistical machine translation, you can track down the rule that gave rise to this word, whereas in neural machine translation, there are no explicit rules. There is no feature engineering. There are no explicit rules that you've coded in, right? So that's the idea. Thank you for clarifying that. Yeah. NMT is difficult to control, and you can't specify rules or guidelines for translation that in some cases might make things easy. Like all of these professional linguistics, they spend their whole lives, their whole careers figuring out all the special rules that help you to you know, translate, take apart the English language. Like, you know, if you have a Q, then you're always going to have a U following it, and so on. These are rules that, that's just a simple rule, but, you know, there are lots of combinations of English words that always occur together, and that helps you to compute probabilities of bigrams or trigrams or fourgrams. If you use this specialized knowledge, you can put in rules that help you, but you can't do that in neural machine translation. Yeah.
Yeah, my question is, so with this disadvantage of NMT in regards to interpretability, so one maybe in some domain like medical field, we definitely go to SMT, right? If we need to do machine translation, because it's a kind of field that needs to have a kind of interpretability issue with them.
You know, I don't know the
provided,
answer to that. Yeah.
Yeah, not really, because these days you can find enough medical documents themselves, and it's just a matter of training on that data set. So
plus, I think
SMT is techniques, or at least feature engineering techniques, have receded, if not completely disappeared. It's still there, but in very, very less. Even in legal, medical, and stuff, it's all moved over to neural because of the fact that you don't have to, we are a lazy species. We just don't like feature engineering a lot.
And the idea that interpretability the idea is that the idea she said is that NMT is less interpretable. She didn't say it's not interpretable. People are working really hard right now on ways to get interpretability for neural machine translation models, just as they are for you know, for CNN models, you know, for in computer vision, and a lot of progress has been made. I haven't been keeping up with it, but I've noticed many papers coming out about interpretability in neural networks. So it's not necessarily true that, you know, neural networks aren't interpretable.
Yeah, there's something called Lime and SHAP and some new techniques out which are used for interpreting the text, the RNNs, and how. I don't know if there is something similar for transformers, but I know that at least for RNNs, there were a couple of methods that I had come across.
Yeah, the one you mentioned, SHAP, is really interesting because it's based on mathematical game theory, and it's at least in the context I'm familiar with it, it's in like a tabular problem. So you have features, you have tabular features, and for every decision you made, like if you for example, you have something that's very sensitive, like, or that's very crucial, like you have to decide, given a patient's data, whether that patient needs surgery or not. So that's a really, you can imagine, a very crucial decision. Now with SHAP, you can look at all of the features, all the measurements they made on that patient, and SHAP can tell you which, it can make the decision, this patient needs surgery, and then it can tell you which features were the most to blame, quote unquote, for that decision, right? It can tell you the degree of involvement of each feature for the decision. So a doctor can then take a bird's eye view and decide whether the decision makes any sense to him or her, if that's clear. The exciting thing about SHAP is it's an optimal way to assign the blame, you know, among all the features, and it's derived from game theory. So that's a really great breakthrough, and that just happened in, I believe, 2016.
Ah, interesting, because I haven't yet come to explore SHAP, but Lime, which sounds very similar, and I do remember it also came out in 2016, and there essentially you're given scores for each of the keywords that are influencing the decision for choosing a certain class, and you are also able to remove the word or change it and see how it affects and which class it jumps over to. So it's very similar concepts. Yeah.
Yeah, you're right, and I think Lime was a big deal when it first came out, and I think that SHAP has mainly displaced it, but I'm not sure about that. What I've seen is that SHAP is better, is regarded to be better, and I'm not sure. I think that Lime is. I don't know enough about Lime to say for sure, but the L in Lime is locally, so I think they're making a local approximation for the weights that they give to each of the features. So yeah, but that's something that's be interesting to look up. I think though that SHAP is now considered to be the method of choice.
Yeah, it's local interpretable model agnostic. So yeah, it can work for any model. You just need the
that's the cool thing, is like when you learn random forest, one of the exciting things about random forest is that it can predict feature importances, and it does this by internally. It comes up with scores that tell you like how important is this feature, and one way to get these scores is to take the feature and randomize it, and then run the model and see if the accuracy takes a hit. If the accuracy doesn't take a hit, then that feature wasn't important at all, because giving it gibberish for the values of that feature didn't make any difference. But on the other hand, if scrambling up the values of the feature and then running the model gives you a big hit in the accuracy, it means that feature was really important to in the determination of the classification. So that was something specific. That feature importance thing was something specific to tree models, random forest models in particular. But the SHAP model and the Lime model, when they came out, were exciting because they applied to any model, including neural network models. So yeah, so now you can get, and so importances were considered, were basically a first step at interpretability for tree models, but the other classical machine learning techniques didn't have anything like that. But then they came out with Lime and SHAP, which could be applied to any classical machine learning technique and deep learning techniques as well. So that's a great step forward. Okay, then she talks about how you evaluate machine translation. How do you tell whether you did a good job? And people have come up with this thing called the BLEU score, bilingual evaluation understudy. I'm not sure. It doesn't make sense to me. That phrase itself needs translation. But I'm excited to look at assignment 4 because we're going to learn, we'll actually get to grips with it, and instead of just seeing the definition of it as we're going to see today. So the BLEU score compares the machine translation to one or more human translations, and then computes a similarity score based on n-gram precision. So it looks at unigrams, bigrams, trigrams, and 4grams, and then also imposes a penalty if the translation is too short. And so she says that BLEU is useful, but it's not perfect. I'm not sure if I think BLEU is still basically regarded as the benchmark, as the benchmark evaluation for language models. Is that not so?
Yeah.
They haven't figured out a better way yet, but I'm sure people are working on it. So she points out that there are many valid ways to translate a sentence, and a good translation can get a poor BLEU score because it might have a low n-gram overlap with the human translation, but might still be a good. In other words, it's looking for mappings between pairs of words, and as we saw in French, even in French translations, sometimes 4 English words get translated to 2 French words, so there wouldn't be a good mapping in that sentence between pairs of words, and so that's where BLEU falls short. Then she points out this chart, which really highlights how neural machine translation has just come in and taken over the field. So here is phrase-based statistical machine translation, syntax-based statistical machine translation. I'm not sure what the difference is. Does anybody know what the difference between the red and the blue bars are? So syntax implies that maybe they've input a whole bunch of grammatical rules into the system to make it better. But anyway, we can see the comparisons over the 4 years between 2013 and 2016. So phrase-based is better. Phrase-based is better than syntax-based. All of a sudden in 2015, syntax-based is starting to get better. There's sort of a slow, gradual improvement. Syntax-based is both methods of statistical machine translation are advancing, but they're advancing at slow rates. And then all of a sudden, neural machine translation blows everybody else out of the water. It's introduced here, and then within a year or so, 2 years, I think she said it was introduced in 2014. 2016, Google Translate, it got so good, so much obviously better than the other techniques, that Google Translate threw away their statistical machine translation model and just went whole hog on neural machine translation. So here it is, 2014, the first seek-to-seek paper. 2 years later, Google Translate switches from statistical machine translation to neural machine translation. So SMT systems, supported by a huge army of engineers over many years of research, was beaten by neural machine translation systems trained by a handful of engineers in a few months. That's pretty much summary of the thing. They basically almost put linguists out of business. Okay, so is machine translation solved? She says no, there are still a lot of difficulties. One of them is out of vocabulary words, domain mismatch between train and test data. And this, I guess when she made this lecture, it was 2019, and Jeremy's contribution wasn't recognized at this point. But Jeremy's contribution essentially allows you to solve the domain mismatch between train and test data, because instead of using Wikipedia data to train a medical database, you can just start with medical. You can do what do you call it? The transfer learning between transfer learning to learn a better language model for medical documents, and then you can train your translation on that. So the domain mismatch problem is no longer a large problem here because of Jeremy's and let's see, the fellow who wrote this paper with him, I forgot his name.
Reuter.
Yeah, Reuter, Sebastian Reuter. They showed how to implement transfer learning in NLP. Transfer learning was famously implemented in computer vision in 2012, I think, at the ImageNet competition. The idea is that you can take a general purpose language model trained on Wikipedia, and then using that, you can train a special purpose language model based on some corpus of text that you're interested in, like financial documents or medical documents or mathematical documents and so on. And you can get a special language model just based on the specialized field that you are interested in, and then you won't have this domain mismatch.
Does that apply as well, though, to machine translation? I can understand that, yeah, for like normal NLP, but if you've trained your network on your parallel data, but then you come to a test set where it doesn't have the parallel data for the language translation, does Jeremy's stuff help with that?
Yeah, no,
well,
I think there's still limitation, and that limitation still applies because the multi-step process that Jeremy is talking about of originally training on and then fine-tuning on, for example, something, you still need the parallel data when you fine-tune for translation. So I think the problem still remains, maybe reduced, but not eliminated, to your point.
But
Steve.
you could,
I think it's a good point.
But I think you could, so if you're interested in applying a language model to, let's say, medical data, you could take French medical documents and train a language model, you know, a general language model, and fine-tune it on French. Well, no, I mean, I guess you would have to produce a set of parallel documents in French medical documents and English medical documents. So if you started with that, then you wouldn't have a domain mismatch problem, right?
Yeah, I was thinking more if you trained
on.
Yeah, if you trained both of them on sort of like, say, Wikipedia, but then you wanted your test situation to be on medical documents, but you hadn't had parallel data with medical documents.
Yes, that's a good point.
Will that
That's
work?
a good point. That's a good point. It will still be a domain mismatch problem.
Maybe training just the decoder part as a language model on your French documents, which do not have the translation. Maybe that could help, right? That could help generating better results.
Yes, help, but not eliminate. So that's why I said it reduces, but doesn't eliminate the domain mismatch problem, as Steve was kind of alluding to. So yes, it reduces the techniques to reduce, but it still remains.
Okay.
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 Yeah. Any other questions at this point? Okay. So finally, she points to one big problem for machine translation, and that is maintaining context over longer text. We alluded to this before. You know, you have to, the longer your sentence gets, the more connections that the RNN has to remember among the words. Like if you have a very long sentence, say 20 or 30 words, the first words, you have to maintain some sense of context. The first words all throughout the whole sentence. And that's what they mean by maintaining context over longer text. And that's a problem because RNNs are sequential, and there's a bottleneck, and they're actually limited as to how long they can remember, especially because of the vanishing gradient and exploding gradient problem. They don't do well with really, really long sequences. And then the other problem is low resource language pairs. I guess that means where you're starting with not very much domain knowledge. You don't, like, for example, if you're if you're trying to translate to some obscure language in, in some obscure dialect where there aren't that many speakers of that dialect. So if you're translating from English to some, let's say, Native American language where there aren't very many speakers of that language left, so you don't have a lot of parallel data. You don't have a lot of sentences that you know of, that translations between that Indian language and the Native American language and English. So I think that's what they mean by low resource language pairs, and there's a lot of those. The major languages, of course, don't suffer for resources. There's lots of German speakers, lots of Arabic speakers, lots of French speakers, English speakers, Chinese speakers, but there are languages that don't have a lot of people working in that language and English, for example.
It's more related to the documents, because there are lots of speakers. It's just the availability of documents.
Good point. Yes. Yeah. Good point. In electronic form. Yeah, that's a good point.
For example, you have a large open source corpus of parallel texts from the European Parliament, because there you need to actually have protocols in all the languages. So there you have actually also quite big parallel corpus for relatively smaller, or countries with not that many speakers. Wow,
that's interesting. I didn't realize that. So, like, I don't know, is Romania in the EU? That's a relatively small country. Czechoslovakia, all these different Slovenia, small countries that are
exactly.
They're in the EU, and they are represented in this parallel corpus. I didn't know that. Interesting.
It's also in this opus. I think they also reference to it. Somebody posted it in the chat before. This parallel corpus.
Sketch Engine also provide parallel corpus.
Say that again, please.
Sketch Engine, I share it there. They also provide corpus for low resource language. Sketch Engine.
Oh, okay.
Yeah. So
it's called Sketch Engine. Sketch Engine. Okay, let me see. Let's see. Oh, working with text. So parallel corpus, Sketch Engine. This will be interesting to look at. Yeah, but the point is that parallel corpora are essential for language translation. You got to have these sets of parallel sentences and phrases and so on. Finally, let's see. Common sense, language, the machine translation still doesn't understand common sense. I think that's still true. Yeah. Paper Jam, translating it from English to Spanish, mermelada de papel, paper jam. So that's interesting. I think I don't see a way for that, unless you, pardon?
You don't see a way for that to happen.
Yeah, I don't see a way for them to. You have to encode special. The only way to do it is to encode special rules for slang, things like that.
So can machine have a common sense?
Yeah.
I just checked actually, and in Spanish it still says, because the course is from 2019, right? So in Spanish it still says marmelada de papel.
If you translate it in Google?
Yeah, but in German it actually gets it right.
Oh, interesting. So I wonder how that worked.
Yeah, I don't know, maybe Paper Jam was like in the, parallel corpus the model was trained on, there were enough instances of it.
Yeah,
so
maybe.
It could pick it up, I guess, and in Spanish, I don't know.
Maybe the Germans use a different word. Maybe jam translates directly into German and into meaning that something is wrecked, jam.
Yeah.
So maybe it doesn't translate directly that way in Spanish. I don't know. But that's interesting. So some languages that they don't have a problem going from paper jam to a sensible translation.
I just look at English to Chinese. It's completely wrong.
Interesting. All right. Let's see. She also points to a problem of bias.
Yeah.
Given some Malay sentences where gender is not specified, and English translation somehow puts in the gender, and it could be construed as to say women are only good to be nurses and programmers are men. Do we have a Malaysian speaker online here? Someone was laughing, so I thought they may have been a Malay speaker. Okay. Uninterpretable systems do strange things. So this is really weird. Translation from Irish into Somali. I don't know where that came from, but if you put that into a language model, Somali to English language model, it comes out as a Bible, something that looks like the Bible. And she pointed out that a lot of low resource languages, they still have the Bible. Almost every language has the Bible. And so if they use that as the corpora, then everything comes out sounding like the Bible.
So initially in the lesson, when she had brought this up and she was saying Somali, I was very confused because all I was seeing there was translate from Irish. But then later I saw that up there is Somali as specified, but apparently Google is deciding for itself that it is Irish. And then, yeah, it's like, wow, there's like a lot of things going on there, because I don't even know at that point if Google is now even considering Somali at all, or is it just directly just overwritten it with Irish and then doing it. So yeah,
I don't know. That would be fun to do some experiments on that. Yeah. So so NMT is one of the most important tasks in NLP. And let's see, many improvements on the vanilla seek-to-seek model that we looked at today. But the major improvement is called attention. And so then she has the third section of the lecture all on attention. So the problem with a seek-to-seek architecture is actually memory. It can lose memory of the early words in a sentence. So it has to capture in one vector all the information from the vector that gets passed on from the encoder to the decoder is the last hidden state, and that last hidden state is a vector that has to have in it all the information about connections among these words, all the way back to the beginning, and that's hard. So in that way, RNNs aren't a perfect solution to the language translation problem. So the idea of attention, which I think also came out in very recently, maybe 2014, or does anybody know for sure? Maybe 2016. Developments have been really fast in this field lately. But the idea is that instead of going through the connections in sequence, you can go through them in parallel, somehow maintain the state in parallel with some kind of an attention vector. And so she shows it with diagrams. First, you start with a source sentence, and you take a dot product of the start vector with each of the source encodings in turn. You calculate all these dot products. Then you take a softmax to turn the scores into, so these are the attention scores, the dot products. And then you take a softmax to turn these scores into probability distribution, as we know how to do. And then this tells you where the attention distribution is. So the one with the highest score is the one where most of the attention was focused on, and translated into English, that means that it was the most important word in the sentence. And you do this with each time step in the decoder.
Can someone provide an intuition of why you do the dot product?
Well, because the encodings are themselves a mapping of the word into a high-dimensional space, and so that's a common technique to find similarities in among words. Is you take the dot products, or you take some kind of a measure that involves the dot product. The dot product is a measure of similarity, because if the dot product is 1, if the two vectors are the same, the dot product is 1, and if they're completely different, then the dot product is 0. And if they're somewhere in between, if the dot product is close to 1, that means the words are similar, and if the dot product is very small, the words are dissimilar. Does that make sense?
You're using the word from your decoder, that is, for example, the start word or the subsequent word as you let it progress, and figuring out for that word in the decoder, what word is it paying is that word paying the most attention to, which is translated as for that word in the decoder, which word in the encoder is it most similar to. That's where the similarity of use of dot product for similarity is the stand-in for quote attention. But there are other attention mechanisms or other mathematical equivalences that you'll see in a minute.
The important thing is this is something you're learning, right? It's not something that you know beforehand. So there's a weight matrix hidden over there that you'll see in the further equations. It's something that you learn.
Yeah, something that
it's not something that you get beforehand by just taking a dot product of two things. You're not going to get something as a high number or a low number. That's going to be random. It's the W that kind of helps it and the process of training as to what to pay attention to.
Right. So once you have the attention scores, you can use softmax to get an attention distribution, and then you can get let's see, the attention distribution. That I understand, but then mapping that to the attention output is basically just giving, I guess it's just giving the score, giving the, I guess it's just adding, multiplying them, or is that how it is? Or it's a weighted sum.
You multiply each of the encoder RNN values by the weights in order to compute that attention output. So it's the weight, you'll see that in a minute as she goes through.
So actually, if you take this a step back, if you remove attention, it actually kind of solves the problem of the bottleneck, right? The problem with the bottleneck is you're just taking the last hidden state. But if you look at the same diagram and remove all that stuff in blue, and let's say you just average those 4 red values, you still have information from all the 4. Attention is like one level higher than that, that kind of helps you in the direction of paying attention to each of these words now.
Yeah.
So you're saying that in some sense, attention is making use of not only the last hidden state, but of all the
like
previous
that's not what exactly attention is doing. Attention is doing one level higher than that, right?
Yes.
Yeah, exactly.
But it's doing,
yes.
but that's a good point you made, Anand, right?
Correctly, yeah.
Yeah, it's a good point you made that if you strip attention down even before, it's already improving on the seek-to-seek model because it's using more information that's just in the hidden state. It's also using information in the prior states, but now it's using that information in a very smart way. So that's the attention model. Now, the attention distribution is used to take a weighted sum of the encoded hidden states. So this distribution then is used to sum up these hidden states to come up with the final state. In other words, instead of just taking the hidden state as the output, you create a new output that depends on all of the previous states weighted in this way, and you take a weighted sum, and that's the prescription for computing the attention output.
And the attention output is computed for each step or each word of the.
Right, so it'll go on to the next word. But notice what happens here. For example, in this case, if you didn't use attention, your hidden state would be the only thing that gets transmitted into the decoder. And the hidden state would probably tend to be dominated mostly by information later in the sentence. But when you use attention, in this particular case, it gives more weight to the word at the beginning of the sentence, il, which is he. And so the new attention output is doing something different. It's able to recognize that this is the most important word in the sentence. So it's not going to be dominated by the words towards the end of the sentence.
So, but why? So if I was doing a translation, it wouldn't have occurred to me that he was the most important word in a sentence.
Yeah, I just one thing before we move on. It's important to understand that it's not that he is the most important word in the sentence. That's why I keep repeating that he is the most important word that the start word is paying attention to.
Good point. Yeah.
It's not the most important word in the encoder sentence. It's just the word. I mean, again, it's an example. It's the word that the start word is paying the most attention to. And if you go to the next word in the decoder, that word will pay attention to a different word. So you can't say the most important word in the sentence. It's for every word in the decoder, what does it pay attention to? And that, as Joseph and Raquel have been both pointing out, is improved to be more than defined by just the last word in your encoder. If you go back a couple of slides, Joseph, you'll see that the information bottleneck diagram is very important to show what attention back there. Now, in a traditional RNN, what you get into the decoder is just that last edge or input state. And that is the information bottleneck, because all of your words in your encoder have to be eventually factored in through this single hidden state. And as Raquel and Joseph have both pointed out, the attention mechanism relieves you from that, takes it to a higher level, and now you get to determine through some mechanism, there are different mechanisms of attention, for each word in your decoder, what does that word pay the most attention to? And in this case, the start pays more attention to the first, and then as he advances it, the next word pays more attention to whatever the entire word is, and so on and so forth.
That's a really good point. Thank you for that, Srinivas. So to answer, I think it's John that asked the question, right? So for the second word, so for the first word, the most important word was he. So I mean, you're right to ask, why should that be the most important word? It's only the most important word with respect to figuring out the first word in the translation, right? He. So it makes sense that the translation should have a word that means something like he, because he is a subject. Then the next word, so after you figure out that the first word should be he, then what word is he paying attention to, and what words is he paying attention to in the input sentence? And he is the subject, and the subject pays attention to the verb. I mean, it's most likely to need to be closely related to the verb in the sentence. So that's why the probability distribution changes. And then, as Srinivas pointed out, this gets done at every time step. You repeat this process of finding the similarities between that particular word in the decoder and each of the words in the encoder, taking the dot product, finding the similarities.
Sorry, one more point to add here. I think it's important to remember attention is trying to solve the alignment problem, right? So if you have a 1:1 correspondence, like if one word corresponds to one, like how you pointed out L and he, there's nothing so great about attention. It's pointing at the same word. Attention really starts shining when it's the many to one or the one to many, that kind of thing. Because then you have a problem of alignment. You can't do like, okay, this third word corresponds to this third word in your original language. It's that the third word has a bunch of,
and we'll see it as we go here. So the point you're making is here, where there isn't a one-to-one correspondence, and the attention mechanism is able to keep track of that. In each case, it looks at this word and says, okay, what are the words that are in the input sentence that are the most closely related here to this word, and it finds that atakte, throwing a pie, is the one that's the closest. So it's not forcing you to translate word for word, but neither does the RNN really. Neither does the seek-to-seek model without attention. It knows how to do the one-to-many or many-to-one or many-to-many alignments, right?
But still, the alignment is the problem over there, right? Attention mainly, I think there's a slide which covers that, like the main purpose of attention is kind of like to deal with alignment. I don't know, that's what I thought. If I'm wrong, someone please correct me.
Yeah, no, it's just more than alignment eventually when we, if you interpret attention, then it does more. But in this instance, yes, she does emphasize that it helps with alignment as an example, but it does more than that. Eventually, you'll figure out that it does much more things in a linguistic sense than just parallelization and that's just alignment. But it is a good point that it significantly contributes to helping address the alignment issue.
If anyone has any resources that has helped you understand attention a bit better, you could post on the chat. I'd appreciate it.
Yeah, when we get to the transformers, then you'll see, because it's much better understood, as with many things, when it is actually applied.
Cool. Yeah, I think that Chris Ola has a good blog on that. But yeah, we'll post. I know Srinivas has a lot of resources that he's used, and I can remember some from the Fast AI class. We'll post some of these on the Slack afterwards. Okay, John?
Hey, Joseph, can you go back a couple of slides? There was one specific point that I wanted to look at, if you go.
Okay, sure. So
I think it's a second slide of this. Yeah, so this one, the box, the pink box on the right. Yeah, so what is exactly happening when she says sometimes we take attention output from the previous step? Is it not like something that is always done?
That's a good question. Sometimes we take attention output from the previous step and also feed it into the decoder along with the usual decoder input. So normally you'd put he in here, but she says you're going to feed the attention output. I didn't even notice this. Apparently they do it in assignment 4, so that's another reason to look at assignment 4. Yeah, I'm not familiar with that idea.
Okay.
This Anand, right? You're asking the question? Okay, I recognize your voice, Okay, thank you for that. Good point. I didn't.
It seemed important too, because it seems like it's necessary for assignment 4. So.
Yeah, don't let her slip anything by us. We have to figure this out. I saw a paper recently. I didn't read it, but I want to. I mean, we've all seen papers that we want to read, and we put them on our list, and then they just never get read. But there was a really interesting paper that came out in the last couple of weeks, where they use attention to improve object detection.
If I might, Joseph, to address another question. So in the previous thing where the box was on top, it basically says for that particular word, you use the attention of that word with all of the encoder states. What she is also saying at the bottom, if you just go back one click, or maybe to the prior, there. So this particular box says, concatenate the attention output based on what you have just calculated for the start word. Now, when you go to the next word, what you do is you take this attention that you have calculated for start and concatenate that with the, if you click now,
I see, that makes sense.
One more down.
Yeah, that makes sense. So that's
now you concatenate with he and provide. So the attention output from the previous step is concatenated with he and sent up. That's not always done.
And the reason for it being done is?
The reason it's done is it helps, gives even more context to he. You provide directly all of the attention knowledge you have. Not only remember that the output actually.
No, my question more was like, why is it not done always? Why only sometimes?
Yeah, that occurs to me too. That's a good question.
Don't know. We'll think about
maybe compute power. Maybe it just doubles. It doubles the compute requirements, I guess. But yeah, it's because you have to concatenate. You have to concatenate. So you have double. You have a vector that's twice as big each time. That's
then the question.
The only guess I would have is it may not always give you the improvement that you seek, or that it may not always be all that helpful.
Yeah. So then my question is, how do you decide?
I guess you try it with and without and see what happens.
No, I mean, this is happening inside a neural network, right? So I'm trying to understand if that's also something that is learned, or it is something that is programmed.
No, that's something you choose to do or not do.
Okay.
Yeah. So if you have a problem to solve, then you can write a neural network that concatenates the attention with each input word, and then run that, and then run the same thing with one that doesn't concatenate, and see which one gives you the better answer. And if the improvement is not worth it, and the time and the compute time is much greater, then you say, all right, well, we don't need this. But
yeah, it looks like it's one of the hyperparameters. I wonder what it's called, but yeah, it looks like it's a hyperparameter.
Thank you both for bringing that up. That would have gone completely by. That's a very important thing here. So thanks for bringing that up, both of you. As I was saying, I saw this paper. I didn't read it, but they figured out how to use attention to improve object detection. And what they do is they use the attention mechanism over all of the objects that were detected in each frame. And so they use the attention mechanism to remember connections among those objects. And that helps to detect those objects in the next frame. I think the method is called DETR. I'll post the paper, the reference to the paper. So attention is turning out to be something much more general than just an NLP technique. It's now being used in object detection in computer vision as well. Okay, then she talks about implementing the equations. We don't have to spend too much time on this, but you know, standard vector language, right? The thing about attention is that all of the dimensions of the hidden states and the encoded states and all that, they're all the same dimension. That makes things simpler. So you can always take dot products between encoder states and decoder states, and that's what's happening here. And remember, a dot product maps two vectors into a number, into a scalar. Sorry. Well, this isn't. Let's see. Yeah. This. Oh. Okay. So this is dot products of. This is many dot products. It's a set of. It's a series of dot products, and so it's a vector of length n, where n is the number of states. Softmax gets converts this thing. It also maps an n-dimensional vector into an n-dimensional vector. Then you sum up. Remember, you have to take a weighted sum of the encoder states to get the attention output, which is now mapped to an h-dimensional. Let's see, what's h? Not sure what h is here.
It's the dimension of the hidden state.
Hidden state dimension, okay. And then the last step, concatenate attention output with the decoder hidden state. And that's what we talked about previously. So now you've doubled the length of your input vectors. Okay, why is attention great? Solves the bottleneck problem, helps with the vanishing gradient problem because it provides paths, provides shortcuts between states, between words that are far away. Instead of having to go through the entire process of backpropagation to get from the last word to the first word, you now have shortcuts to get there, and so it helps with the vanishing gradient problem. Provides interpretability. By inspecting the attention distribution, you can see what the decoder was focusing on. Soft alignment, I'm not remembering what soft alignment was.
No,
soft alignment is
many, highlighting.
Yeah, many to one to many, so on, comes out as a free benefit. We never had to explicitly train the alignment system. The network just figured it out by itself. I'm not sure how that differs from an RNN. Sorry, from the seek-to-seek model. Why is that different than the seek-to-seek model? Isn't that the same thing in seek-to-seek, that you get the soft alignment for free?
No to the details, but the first order, my reaction would be that in seek-to-seek, again, you're limited by what you transfer. It's only the final word that you transfer, so it's not a hidden state, right? The one single hidden state. In this case, you're pushing, you're allowing multiple words from the encoder to influence each word in the decoder. So that helps with the alignment. Maybe it
improves. It gets an improved version of soft alignment.
And especially multiple words, right? And no, maybe reckless more thoughts.
It's that same hidden state that goes into your decoder, right? But if you think about it in terms of when you use attention, for each word that you're trying to predict, you're not using this hidden state. In fact, you're taking this weighted average for all of your vectors in your encoder state. So that, if you think of that as your new hidden state, it keeps changing for each word. So that's where the soft alignment is happening. The weighting is changing, and that is taking care of the soft alignment.
And you're taking the weights of all of the words rather than just at the last.
Yeah,
word,
compressing
right?
everything into that last hidden state.
Yeah.
So it's kind of changing every word you're trying to predict. The soft alignment is happening because the weighting, because of your sigmoid, softmax, sorry, keeps changing for each time you kind of try to compress this encoder hidden states.
So the attention mechanism is essentially soft alignment. It's just intrinsically, it is soft alignment.
Right.
Yeah. Okay,
So
great. That's a great point.
I'm still not completely sure how that is different from the without attention model. I mean, okay, I get the mechanism might be different, but I don't know why it's called out as a benefit, because it is still, the alignment is still happening without attention also.
See, in the previous case, if you're doing, how is the alignment happening? You have no alignment. There is no correspondence, right? Because there is no weightage. In sense, you're not giving equal weightage, but if you use, because it's all kind of compressed into that last hidden state, right?
Yeah, it's all in the, that's all you get about, for alignment, all the information you get is the hidden state.
So assume that is like kind of equally splitting it up for all the words, which is not the case. But if you even assume that, you're not getting any alignment, right? If you do like 4 words and you're breaking it up into 0.25% for each of them, there is no alignment happening there. But now when you bring back when you bring attention into the picture, this 0.25, these percentages keep changing. For each word that you're trying to predict, one will be like 0.7. So you're paying more attention there, and that is taking care of alignment. Wherever you're paying more attention, that's where you're basically dealing with alignment.
So it's implicitly adjusting the alignment at every word. You're getting sort of a built-in soft alignment because of the attention mechanism, because that's what the attention mechanism does.
Right. And key thing again to kind of remember, at least that took me a while to understand, was that this is something you're learning. It's not something that you're given beforehand.
Yeah.
Right.
That's
you have a
really
key, you
excellent,
have a query, and it works like that. Yeah.
That's a really excellent insight from you. I hadn't thought of it that way, but that's a really good way to think of it. Yeah, it's very helpful. Thanks, Rakil. Okay, attention is great. Attention is general. Attention is a great way
just
to.
One question. Can I have one more question, Joseph?
Sure, absolutely.
I'm just wondering, is the attention vector then being fed into the RNN with attention into the decoder part at every time step, or only at the first time step as before?
I think it's every time step. That's what we saw. Let's see. Here's the. So at each word, you can actually see this as a cartoon. Okay, it's first word, second word. So every time the attention output is being adjusted and fed in. Let's see, attention output.
It's computed and fed in at every.
With the option, yeah, and with the option to take it into the next word, right? I mean, that's what we said. Yes. You could concatenate that attention output with the word, and then stuff it as the input to the next level. So yeah, the attention at each time step can be incorporated and is incorporated into the translation.
All right, thanks.
Good question.
If you think about that intuitively, that's what you're trying to achieve, right? For each word, you're trying to see on your input side, what word should you pay more attention to? So if you can pre-compute that and hold it like beforehand, then it kind of sits like the same problem with the without attention. Everything is sitting in just one hidden state.
I guess it would give it more flexibility still to look back in a more flexible way, but you certainly wouldn't have the strong benefits of attention.
Exactly. Right.
Yeah, because with the RNN, with the hidden state of an RNN, you get what you get, and maybe it did a good job. Maybe it was a short sentence and it did a good job of encoding all the connections, but maybe it was a tougher sentence, and it was a grammatically complicated sentence, and it didn't do such a good job. Whereas with the attention model, is sort of tailored to each. In other words, it adjusts itself on each word and takes into account all the context of that word. So I mean, it's a thing of beauty. I think this attention mechanism.
The other very critical thing to understand, because it becomes like, crucial because of the verbiage used in transformers, is keep in mind that every word of the decoder is also a factor in determining the attention that is computed for that word across all of the words in the encoder. So as we'll see in a minute, the reason I emphasize this is the word in the decoder, the start or the he or the hit, is actually becomes the query that you then impose to find attention across the set of your encoder hidden states, which become the values. So the query and the value language is taken over into transformer and is often confusing. But if you understand it here, then you will be able to translate it easier when you apply it in transformer. The query is the encoder word in each case, and the values, the query is the decoder word in each step, and the values are all of the encoder hidden states.
So the query is he, is this word.
Correct.
And then the values are all the attention, or the attention distributions.
The red ones, the red ones.
No, the red dots down below the encoder RNN.
Oh, these, okay.
Over
these
those
are the
values, you get the query computed over those values, gives you that attention output.
Okay, right. So query, values, attention output.
Yeah.
I mean, it's called Q, V, and A, right? In the
yeah. There is a key, but we won't bother right now with it because that's just to separate the keys and the values like a dictionary. But let's not go there right now. If you just understand query and values, you're good.
Query, values.
And the keys are simply the words in the encoder, no? Then in this case also.
The words in the decoder, right?
Sorry, could you repeat the question?
The keys are then the words in the encoder, right? Because you get your attention score by or is it like too much in like kind of changing
because the keys and the
of transformers?
Let's wait for the transformers to see that, because it will just confuse. Right now, think of the values as the red dots, the encoders, and the query is the green dots on your decoder. We'll complete the key picture when we get to transformers.
Okay, so I don't think she's got very many slides left. So attention is a general technique, given a set of vector values on a query. Attention is a technique to compute a weighted sum of the values dependent on the query. And that's what Srinivas just illustrated over here. A set of values, query, each word serves as a query in turn. Query, set of values, attention. That's what she's saying. And that's what Srinivas just pointed out. However, you can use attention in many architectures, not just seek-to-seek, and many tasks, not just machine translation. So that's one of the things that I pointed out with the object detection task. They've now figured out how to use attention, how to apply attention to object detection. More general, blah, 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 we just went through that. We sometimes say that a query attends to the values. So that makes sense, right? That is the word in a decoder attends to the values, which are the words in the encoder. Let's see. For example, the seek-to-seek plus attention model, each decoder hidden state query attends to all the encoder hidden states. So that's basically summarizing what Srinivas so well expressed when he pointed out, when he drew our attention back to that diagram. Is everybody clear on this now, after having had it explained? Okay. More general, blah, 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 attention. The weighted sum, okay. Given a set of values in a vector query, attention is a technique to compute a weighted sum of the values dependent on the query. So we've seen that. And I think we'll see it, excuse me, in a lot more detail in homework 4, where we actually get into the details of the equations. The weighted sum is a selective summary of the information contained in the values, where the query determines which values to focus on. So the query determines the distribution, the weights of the values that are to be combined together. Attention is a way to obtain a fixed size representation of an arbitrary set of representations, the values, dependent on some other representation, the query. So this is all just language that says that, a set of a certain n-dimensional space, an n-dimensional space, and attention is also an n-dimensional space.
But it also, I mean, unfortunately, all we have is words or without words and pictures to express ideas which are deep, right? So this is, in fact, the depth of what those words say is, in fact, illustrated by what you, Joseph, gave as an example of attention being used in object detection, and in fact, as we are doing with the Kaggle competition right now, some of us are in the Kaggle group, the segmentation challenge where the UNet infrastructure, and there's a paper of GANs using attention to produce a much better output. And that's the same concept of attention being taken over, which originally came up in the language model, and taking it off to the domain of images, for example. So that words, those set of words, it essentially says, I'm going to represent what is an infinite representation with a finite set, which is the H value or the attention value. And one way to do that is using the RNNs, because again, there is the fixed dimension H. What attention brings into the picture is the fact that you can use the query, which is your encoder state, to determine a fixed length representation, which is a weighted sum of all of the values.
Right. So the decoder state, which is the query, has a certain number of dimensions, call it n. The encoder states, which are the words, they also have the same dimension. The vectors with the same dimension, and then the attention that gets determined in each case is also an n-dimensional vector. So it basically keeps things in that n-dimensional space, and that, I think that makes the problem more tractable because everything is, all of these vectors have the same dimension. All three of these vectors: the query, the values, and the attention. So finally, I think Srinivas alluded to the fact there are different kinds of different variants of computing the attention. We have looked at basic dot product attention. There's other kinds. I don't want to get into the details because Srinivas has a meeting coming up right away. So I'm going to end now, and those of us who want to will move on to the Kaggle meeting. And thank you for being here.